Okay, welcome to Robotics 1. Today's topic is, if you ask me, it's pretty theoretical. And usually I assign this topic for self-study because you can grasp the concept by reading it. But then I thought it might just be a good idea for me to quickly review the important concepts because these concepts are very important when we talk about a robot that interacts with the environment. So, and these are quite important when we study perception, because perception is like understanding where the robot is, what's happening around the robot, and for that we need sensors. That is topic 10. And once we have some sensors, we want to provide the input of the sensors to a control system. And finally, the control system is going to send some controller signal to actuator. So we need to understand what different types of actuators are used. And again, in general, when you are trying to build the robot, we studied the kinematic configuration, we studied the dynamics of the robot, we studied the control of the robots. Now let's look at the mechanical hardware that actually makes up this robot. And again, this is the synopsis of the chapter from Niku's book. So my recommendation to you is either you can read the chapter, or I have uploaded these slides onto Canvas. You can review the slides that will give you the gist of the topic. So the important actuators are electric motors. In electric motors, you have something called as the servo motors. Servo motors are closed loop systems. So what do I mean by closed loop systems? So if you look at a servo motor is nothing but a DC motor. But at the end of the DC motor, you have a feedback element. It could be an encoder or a Hall effect sensor, or it could be a resolver, or it could be any feedback element. So this is servo motor is a closed loop system. Now stepper motor is an open loop system. So what it means is, for the stepper motor, what you have is you have a rotor and you have a stator. And what happens is we energize the stator. So maybe opposite windings of the stators are energized. So the stepper motor gets aligned like this. After some time, you activate the other two. So you activate this guy and this guy. So now the rotor turns, but there is no feedback like whether the motor shaft really turned or not. So what you could do is you can have this stepper motor and you provide the signal and you hold the shaft, but the motor wouldn't know if it really turned or not. Sometimes what we do is we use this direct drive electric motors. And as the word says, it's a direct drive. So you have the rotor directly connected to the drive element. Some robots contain hydraulic actuators. The hydraulic actuator, just like your power steering, wherein what you have is you have a cylinder. This cylinder is filled with oil, and then you have valves on the entry and the exit. Depending upon which valve opens and which valve closes, this piston travels forward or backward, and then you can get this motion. Instead of oil, you can have air, and that will be the pneumatic actuators. And this pneumatic actuators is an upcoming field that is also called as soft robots. When your pneumatic actuators are not hard, which means you don't have a mechanical component like piston, cylinder, but it's all like bellows or sort of soft air muscles. There are different types of actuators, and we will talk about other issues that typically we look at when we study uh, these actuators. Now, what are the important characteristics? Clearly, depending upon the type of robot, whether you have a ground robot, aerial robot, or what task robot is going to perform, you need to be mindful of the power to weight ratio. You need to be aware of bandwidth, how fast or slow that robot can respond. You also have to understand that if that robot is going to work in an environment which is maybe corrosive, or if it has high temperature or other effects that affect the performance of the robot, then you have to make sure that robot has enough rigidity and enough softness. So you don't want a robot that is interfacing with a soft element, for an example, like a human, or maybe you don't want a hard robot grabbing a banana because that will crush it. So what you want to do is you want to kind of make sure that you have enough compliance. That means enough give to the robot. Again, clearly we have to have a power amplification, or sometimes we have to have force amplification, we have to have speed amplification. Depending upon what we need, we can use gear reduction or gear ratios. Now, power to weight ratio is highest for the hydraulic systems. The only problem is you need a separate power plant, which means you need a pump, accumulator, motor, and hydraulic fluid, all that stuff. Typically, power to weight ratio is medium for electric motors, and pneumatic systems are the lightest. That's why the soft actuators are used in rehabilitation uh, use cases. Now, stiff systems are sort of semi-rigid systems. They are more responsive and they are more accurate. They don't deform. They are not flexible. But the issue with the stiff system is, again, you can't just use the stiff system when you are dealing with the surrounding, which has more compliance, which is soft. So sometimes these need selective compliance. When we use gear reduction, the idea is, please understand, power transmitted, if there is no other element that is adding power, power transmitted is constant. So P1 is equal to P2. So, but torque times angular velocity has this product, which is power, can be manipulated either by changing torque or by changing speed. So for an example, T1 omega 1 is equal to T2 omega 2. If my omega 2 is higher than omega 1, then clearly the T2, the value of torque, is going to go down. So by just like you have a car, and if you are driving stick shift, then you start the vehicle in neutral, then put the vehicle in the first gear where the speed is low, torque is high, put the vehicle in the second gear where speed is medium, torque is medium, and then you put the gear in the third or the fourth gear where speed is high. So the vehicle picks up speed, but the torque is low, which means if you have to climb a hill, you have to downshift. And again, when you have a gear box, clearly you have more number of parts, you have more weight, cost is more, there is backslash, noise, inertia, there inertia loads. And then sometimes what happens is, just to get that gear system started, you need to overcome the inertia of the rotating components. Now here is an overall comparison of different actuating systems. So for an example, what makes you choose a particular actuation system? So for an example, if you have to have a robot, you can have a hydraulic robot, you can have a pneumatic robot, You can have a robot where it is driven by the electric motors. It could be a linear motor or a rotary motor. But hydraulic shines when you have large robots, payload is heavy, a high power to weight ratio, stiff system, gear reduction is not needed. You want to have a wide range of speeds, and then you can actually lock the system in place. But unfortunately, there you need to be careful about the sealing, otherwise the oil may leak. It needs pump, reservoirs, expensive, noisy, and all other things associated with a hydraulic system. Now, on the other hand, if you are looking at the electric system, then electric systems are good, and then you can actually look at uh, different uh, types of electric motors, but the compliance is higher. You can use reduction gears. It does not have the issues with the leakage, and they work very good for the clean room where you are working with the silicon wafers and you can't have any contamination. But again, they have low stiffness, reduction gears, and then again, sometimes you need to add some type of braking system and so on. Then again, pneumatic system. Again, in pneumatic system, reliable components, no leaks, inexpensive, low pressure. But the problem with that, you need air filter, pressurized air. Again, you have deformation, low stiffness, and lowest power to weight ratio. This is the principle for hydraulic actuator. Force is equal to pressure multiplied by velocity. Pressure multiplied by area. So P multiplied by A, that gives you the force. And force multiplied by the velocity gives you power. So pressure multiplied by the volumetric change will actually be equivalent of power. And again, you can look at the torque, and the equation for the torque is derived as shown here. And again, we have the equation for the flow rate. The different components of hydraulic system, you can have a linear actuator, you can have a hydraulic pump, you can have a cooling system, you can have a reservoir, you can have servo valves, and all these types of valves, hoses, filtering system, and sensors. Typical hydraulic system, think about your uh, power steering pump, wherein you have an actuator. That actuator is connected to some type of sensor that gives the feedback to the controller. It's connected to the servo motor. There is a servo valve. There is a hydraulic power unit that actuates the forward or backward motion. So you turn your steering wheel, and then hydraulic actuator that actually pushes or complements to your motion. So it provides additional force. Pneumatic devices similar to the hydraulic systems, but you use pressurized system. The only problem with pneumatic systems is hydraulic systems, the hydraulic fluid is incompressible. On the other hand, the pneumatic system air is compressible. So you have to account for compressibility effects. You have to have lower working pressures, and control is hard, but leakage is not a problem because again, at the end of the day, if it leaks, it's just air. It's inexpensive, it's safe, and then basically uh, it can be used for compliant actuation. Electric motors, uh, if you come from electrical background, you will take multiple courses to study electric motor, to control electric motor, to understand the actuation and drive of electric motor. But there are many electric motors. There is AC motors. The motors run on alternative current. DC motors, the motors that run on direct current. There are stepper motors. There are direct drive motors. There are brushless DC motors, and so on. The idea is you have something called as the electromotive force. And the principle is very simple. If you have a current carrying conductor, which is in the magnetic field, that current carrying conductor experiences a force. Now, if you look at the way the coil is shown over the here, the picture is the rectangle. Once you pass the current, you are going to have a force on the left hand side that is going upward direction, force on the right hand side going in the downward direction that will provide the torque. And what needs to happen is once this coil is turned, the, the current direction must be reversed to continue to rotate the coil. And that is called as commutation. So what you have commutator brushes that actually ensures that the current direction is alternatingly changing that continues the DC motor to rotate. Now, there are important differences between AC and DC motor. So DC motor speed control is fairly simple. Change the voltage, the speed is controlled. AC motor speed control is changed by changing the line frequency. DC motors, there are two types of DC motors. You can have brush DC motors or you can have brushless DC motor. Brushless DC motors are something similar to the stepper motors, wherein what you have is you have the rotating magnetic field in the stator and the rotor tries to chase this stator magnetic field. Again, brushless DC motors, because they don't have brushes, there is no arcing, they are long lasting. And in terms of heat dissipation, AC motors, they dissipate the heat much better way. And if you look at the most of the motors that we use, for an example, pool pump, for an example, the fan motor, most of these motors, they are AC type motors. They are usually the wound motors, so rotor is wound. Sometimes the rotor could be squirrel cage, and both of these are very commonly used for applications. And uh, again, if you look at the heat dissipation path in the DC motor, the heat must pass through the air gap. But in AC motor, the heat must pass through the magnets and the body of the motor. So if you look at the pool pump, you will clearly see there will be fins and there will be some additional fan at the back of the motor that is going to push the air through the gap. Heat generation in motor, again, the simple principle is I square R, which is the square of the current multiplied by the resistance. That is the heat generated. And then the problem is as the winding heats up, the resistance increases and that actually increases the heat generation. And many a times the rotor failure or the motor fails because of the shorting of the rotor winding because of the heat. And again, you can change the strength of the magnetic flux, um, but problem with heat is that heat affects the magnetic flux, and actually that actually changes the torque, and then it requires additional current. Uh, so impedances, there is a question on impedance. I need to be okay. Let me talk about impedance. Impedance by definition is force divided by velocity. Now, why is impedance important in robotic systems? Because about 20-25 years ago, Professor Hogan from MIT proposed this idea that the robots interact with the environment in terms of impedances. So I give you an example. Imagine that, say, you have a banana, and what you want to do is you have this robot hand, and this robot hand wants to grab the banana. And now on the other side, what you have is you have an orange. Okay, so you have an orange, and this same robot hand wants to grab an orange. Now, please understand the type of grip that is required to grab a soft object such as banana so that you won't squish it is different than the type of grip that is needed to grab sort of a semi-hard object as an apple or orange. So what this means is this robot is interacting with the task or with this object in terms of the force that is being applied and the rate at which the force is being applied. So what it means is basically the important part here is we need to match the impedance of the soft object and the impedance of the hard object for that successful operation. I'll give you another example. Say, imagine that you have a Honda, maybe Civic, and you have maybe a Hummer. Now, what happens is in this Honda Civic, you have an engine and you have a transmission. In this Hummer, you have an engine and you have the transmission. And for some reason, the Civic engine dies. Okay, so this engine is dead. And for some reason, Hummer's transmission dies. So Hummer transmission is dead. So right now you don't have any vehicle that runs. So the question is, can you attach Hummer engine with the Civic transmission? And clearly the answer to that question is no. Why? Because the power, in other words, torque and speed that is generated by the Hummer engine is different than the torque and speed that the Civic transmission needs. Now, if you think about torque and speed, that is equivalent of forces and velocities. So what that means is the impedance of the Civic transmission does not match with the impedance of the Hummer engine. So what that means is if you want an engine and if you want a transmission to work together, the impedances should match. And that is very important. And impedance matching is a very fundamental concept in electrical circuits. So if you are going to attach one circuit to other circuit, then impedance matching is an important criteria that engineers have to take into account. But for mechanical systems, again, matching impedances is also very important. Now, I give you another example. Imagine you have a person A and you have a person B. Okay. And person A speaks very loud and very fast. So person A speaks loud and fast. There is a possibility that this person B may not be able to understand what this person A is saying. So what would this person B say? This person B would say that, hey, not so loud, speak softly and slowly. So for proper communication between person A and person B, you have to have force and velocity matching. And same thing is the concept of impedance. So impedance matching is very important in communications. Impedance matching is very important in power transmission. Impedance matching is very important, as a matter of fact, in knowledge transmission. So if you have a professor you don't understand, or if he speaks too fast or it's too loud, then probably it may be difficult to understand what that professor is saying. So impedance matching is very important. I hope I answered that question. So in DC motors, they are very commonly used. They are reliable, quite powerful. Again, you have permanent magnets or you can have electromagnets. So, and again, the brushes and commutators are used to change the polarity so that the current alternates, so that the rotor continues to rotate in only one direction. Now, if you study electrical systems, You are gonna study a lot about power and speed and torque, different characteristics. But I want, what I want you to understand is torque of the DC motor. There is a voltage and there is RPM, and these are the coefficients KT and KT square. Those affect the torque output of the motor. And clearly, when omega is zero, uh, well, there is some stalling torque that the motor can sustain. But once it exceeds its capacity, basically motor will start heating up and it can damage. So nowadays you can see these pancake type of motors, which are the low inertia DC motors, and they are commonly used in lot of applications, wherein you can see this long winding is sort of squished, and these are called as pancake motors. Nowadays, there is a frameless motor wherein what you have is the motors are directly integrated into the joint. And please understand these motors are expensive, and gear reduction or maybe a harmonic drive is needed to achieve the performance specs of the robot. AC motors, again, the rotor is a permanent magnet or it could be a squirrel cage. The stator would have some windings. Those windings are charged, and then the field rotates, and then the rotor tries to catch up. There is something called as the synchronous motor, and there is an asynchronous motor. In the synchronous motor, the speed of the rotor, the motor magnetic field runs at the stator magnetic field. In asynchronous motor, there is a difference in the speed. And again, depending upon the application, you can choose different types of motor. They could be AC motors or they could be DC motors. Brushless DC motors, they are commonly used. And again, one classic example is the hard drive. The hard drive that is used in not the solid state one, but the rotatory disk hard drives. They have brushless DC motors. And again, they have electromagnets, and then they have a controller. If you are into RC planes, the brushless DC motors, they actually need something called as electronic speed control. That electronic speed control controls the rotation, and usually you can have a Hall effect to kind of come up with the commutation or to know which coil is to be charged. And these are the direct drive electric motor. Again, the advantage of direct drive is large torque at very low speeds. And again, you can use a voice coil for the actuation. But again, these are very expensive, and they have applications when you have very high torque that needs to be supplied at a very low speed. Servo motors, again, these are DC motors, wherein what you have is you have some type of a feedback element in the back. Again, when there is no load, the speed at the no load speed, the back EMF is equal to the supplied current. When the load is applied, the speed decreases and you have the voltage differential. And this voltage can be measured and used to control the speed. And again, the feedback is also used. And this is the relationship that talks about the torque versus speed. And if you look at a servo motor, this is the schematic of the servo motor. As you can see, this is the coil windings, and you have the feedback element. It could be a Hall effect sensor, it could be an optical encoder, some type of rotary encoder, some type of resolver, etc. In the case of stepper motors are inexpensive. They could be unipolar, bipolar. Construction is similar to the AC type motors. They require a drive circuitry, but they don't need any feedback. So if you go to Innovation Hub, or if you have a 3D printer, almost all 3D printers are using stepper motors. And in the stepper motors are basically you have something called as um, you send the pulses, and depending upon those pulses, you can actually uh, get the motion activated. Now, again, stepper motors are used in low cost applications. So if you have a CNC or a CNC router, stepper motors are used in low cost CNC routers. But if you go to an expensive CNC, then you would use a servo motor. Now, again, in stepper motor, you can have a full step or you can have a half step. So think about it that you have these rotor that has already permanent magnets, and you have electromagnets. So as soon as you supply currents, then the pair of magnets get activated, and then the rotor starts rotating. So depending upon whether you want a full step, you can turn off opposite windings and turn on opposite windings as shown in case B. If you want half a step, then you can turn on all the windings and make sure that it's at the half step. Then you can have alternate south and north poles. And again, that is called as the Hallback array. And that can be used as a rotor. You can have an alternate configuration where you can have 4 plates and coils with tabs. And then you can alternatively actuate, and then you get the motion that you desire. Again, this is the actuation sequence. So you can use actuation and then achieve the steps in the sequence that you want. You can actually, uh, if you look at the stepper motors, there is a unipolar, bipolar, uh, and again, there are different variations of the stepper motors. There are different stepper drivers, and depending upon how you pulse, sometimes there is a concept which is called as micro stepping. So you can actually have a resolution lower than the stepping resolution. So stepper motors is a huge topic in itself, and the idea is they are low cost alternative for robotic applications, but they don't have feedback. And again, you can use a stepper motor integrated circuit that is called as the stepper driver, and you can have a microcontroller signaling the stepper driver on and off, and then that stepper driver would actuate the electrical elements. You can have some type of hybrid stepper motor wherein you have multiple coils. You can have center tapped independent windings. You can have permanent magnet coils, or again, the combinations of different stepper motors. In the case of hybrid stepper motors, the advantage is you can do micro stepping, wherein you can align the various divisions as shown over here, and you can get the resolution which is smaller than one stepping distance. Again, you can actually do the switching the way it is shown over here, wherein depending upon how many switchings you want or how many switchings you are activating, you can control the speed, you can control the resolution, and so on. There are unipolars, there are bipolars, and there are bifilers stepper motors, wherein in the case of unipolar motors, you just need one power source. Bipolar motors require two power sources, and bifilar motors, the coils are center tapped and you need only one power source. These are the different windings of stepper motor. You can see 4 leads. You can count the number of terminals that indicate the number of leads. You can have 4 leads, 5 leads, 6 leads, and 8 leads. Now the torque and speed characteristics of stepper motors, you have something called as the holding torque, which is the torque the stepper motor can supply without rotating. But again, the issue there is you can have inertia loads, you can have the driving uh, rotors, or you can have running rotors. So you want to be careful and just make sure that that motor is capable of withstanding the load. Otherwise, basically the robot would give up, or the load will come down on its own. And then you can, again, with the stepper motors, what you can do is uh, Zener diodes or diodes, they make sure that the current only flows in only one direction. So you can add those diodes to make sure that the motor does not break down. And please understand, even though motors are used for converting electrical power into mechanical power, but if you have an overrunning load, which means if the load is driving the motor, then that motor can act as a generator. And the problem with the generator in voltage is it can uh, burn the circuitry. So that's why sometimes they use some freewheeling diodes or diodes for protection. They protect the current flowing only in one direction. Again, micro stepping, as we discussed, instead of full on, full off, you have sequential on and off in multiple steps. And then you can actually have fractional steps also possible. And stepper motor control, again, this itself is a topic of study. There are actually courses on motor control where you design the converters, inverters, stepper motor circuits, MOSFETs, etc. But the idea is you have the switches like transistors, and you turn the transistors on and off at very high speed. That basically is like turning the mechanical switches on and off. And you have a microprocessor that actually turns those switches on and off. So basically you can send a PWM and the microcontroller would turn on the switch, or basically once it goes, microcontroller sends low signal, which is 0 volts, the switch is turned off. And this is how a stepper driver looks like. And if you look at the stepper driver, it's just like an internal IC chip, integrated circuit. All the ASIC is internal. Usually they have some type of a heat sink that can dissipate the heat because of continuous on and off, on and off. But you have a microprocessor or a microcontroller that is actually turning, sending some type of PWM, and you can send actually flip certain pins on and off that will change the direction of the stepping. Now, microprocessor control of electric motors, that is again something called as the digital control. And what we do is we use H bridge. H bridge is like something like a transistor, and you have a microcontroller that supplies the turn on. It turns on the transistor by teeny tiny amount. So the idea with transistor is you basically have three terminals, and you supply a teeny tiny current to the center terminal, and basically the large current can flow from top terminal to the bottom terminal. There are different configurations, NPN and PNP, but I want you to think about transistor is like an electronic switch. So you basically send an small teeny tiny electrical signal, and the transistor switch opens. And again, transistors are efficient when they are run on full power. But again, the problem with transistors or basically MOSFETs is you are turning them on, off. So you lose a lot of power in losses. The pulse width modulation is used to control the transistors or something called as MOSFETs. You basically send the signals V max and zero. You turn on and turn off the transistor. That actually controls the motor speed. And you can adjust the sequence by controlling the PWM signal that is sent out. H bridge is again two transistors, basically or 4 transistors depending upon whether you want to control the speed and the direction or just speed. So what you can do is you can have these software switches basically from the microcontroller. You send these pulse widths and then you control the speed of the motor. And again, uh, you can do this with simple transistors, but the problem with the transistor is if you turn on and turn off those switches very fast, they can burn out. That's why what we do is we use something called as the metal oxide transistors, MOSFETs, which they have heat sink and you can turn them on and off. The H-bridge control is basically done using a microcontroller. So as you can see in this particular configuration, there are 4 transistors. So there is SW1, SW2, SW3, and SW4, and they are connected to a microcontroller. And what you do is you send the high signal and the low signal, which means you send the 5 volts or 0 volts or 0 and 1. So basically you send a rectangular pulse and that controls which transistor gets turned on and which transistor get turned off. That can control the direction and the speed of the motor. There are other actuators. You can have magneto-rheological actuators. Think about it like you have a magnetic fluid, uh, and then basically you magnetize the fluid, and all of a sudden that fluid changes its viscosity and becomes a semi-solid. Or you can have shape memory alloys, wherein what you do is you provide some type of input, either temperature or current, and the alloy changes its properties, it displaces. Or you can have EAP, electroactive polymers. Again, these are polymers, you supply the voltage and then they bend. And there are different exotic types of actuators that are studied and used. I would encourage you to take a look at Festo soft grippers or coffee bean grippers. So coffee bean gripper. So these are some interesting type of grippers that are used in robotic applications. Now, next part is why do we need speed reduction? As we talked about, the power is going to be constant. So we have to manipulate either torque or the speed. If the speed increases, torque drops down. So with the help of the gear transmission, what we do is we control the speed and manipulate the torque. And again, in the idea is you can have a very small motor that is running at very high RPM. And then if you use a gear reduction, a heavy gear reduction, just like a planetary gear drive shown over here, this is the planetary drive, then that small motor can supply very large torque. Because please understand that small motor is supplying low torque, but the speed is very high, say 10,000 RPM. And all of a sudden you use some kind of a transmission and this speed drops down to say 1 RPM. All of a sudden you get a 10,000 times multiplied torque output. So that is the purpose of the transmission. So you can change the speed. So reduce the speed, torque will increase, decrease the speed, uh, uh, reduce the speed, torque will increase the speed, torque will decrease. And again, you can have the ratios where the gear ratios is again depending upon the type of gear train that you use. The equations for the gear ratios are different. And again, there is something called as a harmonic drive. It's a very interesting concept wherein what you have is you have a wave generator and you have sort of an ellipsoid cage that actually kind of rotates, and basically that gives you a very high reduction at the output. So again, this is just a quick overview of different types of actuators. I would encourage you to review the material, also look at some of the YouTube videos, or try to see how these actuators work in actual practice. And with that, what I would like to do now is I would like to discuss quickly the assignment problem. So I'm gonna try to talk about the assignment problem. Any questions? Any questions on the assignment problem before I start? So that assignment is due today. I'm going to draw the kinematic diagram. So what we have is, we have a revolute joint. This revolute joint is attached to a prismatic joint, and this prismatic joint is attached to the next revolute joint. So this is the revolute joint, this is the prismatic joint, this is the revolute joint. Everyone okay with kinematic diagram? By now you should be experts in kinematic diagrams. Okay, so you are able to do a forward kinematics, then you can do inverse kinematics, and then at the end you can find out the kinetic energies and you can find potential energies. And after you use the Euler-Lagrange, you should be able to find out the Lagrangian, which is the difference between the kinetic energy and potential energy. So T minus V. Any questions here? Now, at this point, what I want you to do is, I want you to quickly look at the assignment that I talked about, and let's see what is given to us. What we have is, we have the first revolute joint, and I'm going to call the first revolute joint as theta 1 and theta 1 dot. Then I have this second joint. Second joint has D2 and D2 dot. These are the joint variables. So joint variables are theta 1 and theta 1 dot for the first joint, D2 and D2 dot for the second joint, and again theta 3 and theta 3 dot for the third joint. Everyone with me so far? Now, if you think about this setup, we can solve this with some set of initial conditions. So for an example, if I were to say my theta 1 is equal to say 30 degrees, theta 1 dot is equal to 0, if my D2 is equal to say 0.25 meters, D2 dot is equal to 0. If I supply theta 3 is equal to 20 degrees, and if I supply theta 3 dot is equal to 0, my question to you is, can you solve the differential equation ODE1 dot m, and can you get me the plots between theta 1 time, theta 1 dot time, D2 time, D2 dot time, and then theta 3 time and theta 3 dot and time. Everyone okay with this? So you have theta 1 t, D2 t, theta 3t, theta 1 dot t, d2 dot t, and theta 3 dot t. Once you see this problem, you are able to generate the plots. Any questions so far? However, if you look at this problem, in this problem, the problem is given slightly differently. What is said is the first joint is rotating at certain speed, which is omega z. This is nothing but theta 1 dot, and theta 1 dot value is given as, let me read here real quick. This is the assignment 5. Yeah, so it's 2 theta 1. Okay, theta 1 dot is sine 0.3t. Now I want you to focus on this. If theta 1 dot t is sine 3t, which means theta 1 as the function of time is sine 0.3t. So theta 1 dot at 0 is equal to 0. Everyone okay with this? So which means the initial value of theta 1 dot when time t is equal to 0 is 0. But as time changes from 0 to a non-zero value, basically it starts spinning at this speed. This speed kind of goes up, comes down, goes up, comes down, goes up, comes down. Then next step is, this is the value of d2. There is a typo, it's not a, that is d2. d2 is given as 2 sine 0.5t. So d2 value, which is this guy, is given as 2 sine 0.5t. That also is like d2 when time t is equal to 0 is 0. Now the question is, how do we add these values to the simulation? The last thing is the value of theta 3 is given as 30 degrees. So this is known. So we are okay with this. The problem is for theta, so theta 1 is not given. So this is 0. Theta 1 dot is sine 0.3t. d2 is 2 sine 0.5t, and d2 dot is clearly the derivative of d2, whatever it is. So the question is, how do we take this into account? So now what I want to do is, I want to show you my MATLAB code, and we will see how we can add these conditions into what we have here. So what I'm going to do is, so as soon as I say d2 is 2 sine 0.5t, I have d2 dot is 2 times cosine of 0.5t multiplied by 0.5. So it is 1 cosine 0.5t. So everyone understood this? So I want you to look at these equations. So I want you to look at this equation. I want you to look at this equation. I want you to look at this equation. And now what we are going to do is, we are going to go on to the MATLAB and change the code. So I will change my screen to MATLAB. So can you see my screen? Okay. Now what I want you to do is, what I want you to do is I want you to look at this ODE1 that got generated. So your ODE1 should be something like this. Is your ODE1 something similar to the ODE1 shown over here? Is will joint P have a rotational kinetic energy? The joint P does not rotate, so it will just have the translational kinetic energy. So, so what I want you to do is use your code after you generate your ODE1. Uh, it should look something like this. Now here, let's look at Y1, Y2, Y3, Y4, Y5, and Y6. Y1, Y2, Y3, Y4, Y5, and Y6 are the states of the robot. So, okay, maximize editor, uh, be with me for a second. Home, preferences, font. Okay, can you see now properly? So your code would look something like this. This would be the code that you generate after running the Euler Lagrange. And this code is going to be super complicated and with a lot of terms. The thing that I want you to focus is Y1, Y2, Y3, Y4, Y5, and Y6. When you look at the run code, you are supplying Y0. These are the initial conditions. So this is the initial displacement of joint 1, initial velocity of joint 1, initial displacement of joint 2, initial velocity of joint 2, initial displacement of joint 3, initial velocity of joint 3. Now, all that being said, I want you to look at the initial conditions that we wrote down. The first joint, the initial value is 0. The first joint initial velocity is 0 at time t is equal to 0. The second joint initial displacement is 0. However, the initial velocity for the second joint is going to be 1, because look at it, d2 dot is equal to 1 multiplied by cosine 0.5 t. So basically this will become 1. Then you have this 30 pi, which is the initial velocity, initial displacement of the third joint. And this is the initial velocity of the third joint. Now here, what I want to do is, first, let's just run the baseline code, which is the ODE1. ODE1 is the code that was generated from the script without any modification. But I want you to note that Y1 indicates the angular displacement of joint 1, Y2 indicates the angular velocity of joint 1, Y3 indicates the linear displacement of joint 1, Y4 indicates the linear velocity of joint 2, Y5 indicates the angular displacement of joint 3, and Y6 indicates the angular velocity of joint 3. So what I want to do is, I want to use ODE1, and then I'm gonna click run. So when I run it, this is the type of solution I get. This is theta 1, omega 1, d2 dot, theta, this is theta 3 and omega 3. So basically this is the third joint. This is the first joint displacement, first joint velocity, second joint displacement, second joint velocity, third joint displacement, third joint velocity. Everyone with me so far? Any questions? I'm looking at the chat window. Any
Can you
questions so
show your
far?
ODE1 page one more time, please?
Say that again.
Can you show your ODE1 M file one more time?
ODE1 M file.
So the changes you made, those were at the bottom, or
No, I didn't make any changes anywhere at this point. This is the ODE1
okay,
file that was generated once you fed in your Lagrangian. What I only did is I added these notes. Y1 is angular displacement of joint 1, Y2 is angular velocity of joint 1, Y3 is the linear displacement of joint 2, Y4 is the linear velocity, Y5 is the angular displacement, and Y6 is the angular velocity. These are the only changes that I made to this code. Everyone with me so far? Yeah, you have to generate ODE1 file using the Euler-Lagrange script, the way we did it for all the robots. Now the question is, how do we modify this to incorporate the conditions that are given to us? Let's once again do a quick recap. The recap is, if you look at the conditions, the angular displacement of joint 1 is going to stay y1. Angular velocity of joint 1 is going to be sine of 0.3t. Angular linear displacement of joint 2 is going to be 2 sine 0.5t. Linear velocity of joint 2 is going to be 1 cosine 0.5t, and so on. So now what I want you to do is, I want you to save this file as ODE1 underscore new. And please change the name of the file to this. So make this change. Save this ODE1 file as ODE1 underscore new dot m, and the first line of the code should be changed to function now should be ODE1 underscore new. And in this code, what I want you to do is, I want you to add T2 is equal to Y1, Y2 is equal to the velocity, Y3 is equal to the displacement, and Y4 is equal to the velocity of the fourth joint. So this would be Y4 is equal to cosine 0.5 times t. Are you with me so far? So the change that we made is we hard coded the value of the angular velocity of joint 1. We hard coded the value of linear displacement of joint 2. We hard coded the value for the the linear velocity of joint 2, and we did not do anything to the angular displacement of joint 3, and we did not do anything with the angular velocity of joint 3. Everyone with me so far? And rest of the code is going to remain the same. I don't have to change any of this code. Any questions? I'm looking at the chat window. Any questions here?
Professor,
Yeah,
which Euler-Lagrange file did you use to generate the ODE1? Because the one that I got does not look like your ODE1 file.
basically, I use the same Euler-Lagrange code that I gave you, but you need to make sure that the Lagrangian that you have found out is the correct Lagrangian.
Okay.
So if your Lagrangian is different than my Lagrangian, then clearly our ODE1 files are gonna look different. But I'm hoping at this point that the Lagrangian that you have found out is correct.
Okay, thank you.
Okay, now the last, what masses to assume for 3 links. Okay, that I think is given in the problem. The next part is go to assignment 5 run, and now instead of using the old ODE1 file, change it to ODE1 underscore new. So if you take this out and save, go to ODE new, save, and then run, and then you will see this plot. And now you will notice some interesting behavior. Please understand clearly the value of theta for the first joint will go on increasing because you are supplying a constant rotation. But check this out, omega for the first link is sort of the sinusoidal. So you will see that omega is changing. But what happens is because of the inertia effects, those values get affected. So basically you see that this omega is sort of sinusoidal. A D2 is the extension of prismatic joint. This also starts at 0 and kind of follows the sinusoidal pattern. And then what we have here is we have the velocity, that the cosine velocity, but that velocity gets affected because of the inertia effect. But at the end, what you will notice is theta 3 and omega 3, you will see these sinusoidal variation and these types of variation. So this is how you would implement your code. And yes, the assignment was extended a few weeks. But if you have turned in your assignment, you can still turn in the assignment without any penalty by tonight. So tonight, 11:59 p.m., please turn in assignment number 5. And to answer the questions related to the assignment, okay, so this is the problem, and I think I solved all the problems. And last part is this part is sort of optional. So even if you don't do 2.5, that is okay. So basically this 2.5 is once you substitute the value of S, and then you should be able to find out the gain value. Yeah, you can turn in the new update, the update your ODE file submission. So you have time till tonight to finish the assignment. Anyone have any questions for me at this point? I will show you the code once again and show you the plots. So just in case if you have any questions, these are the changes to be made. This is like adding constraints, and everything else would remain the same. Yeah, if you do the remaining part of the assignment, you can certainly get extra credit. Okay, if there are no questions, I'm gonna stop here. Yeah, I'll show you the plots again.
Oh, hey, Professor.
Yeah.
How do you do the The rotational kinetic energy was one part that kind of threw me off. Do you know how to briefly solve that, or?
So were you able, so it's exactly the same process we used for the previous robots. What we have to do is for each and every link, we have to find out the rotational kinetic energy and translational kinetic energy, and then add those energies together. The translational kinetic energy, the equation is 1/2 mv square. M is going to remain the same in each direction. So you would have Vx, Vy, Vz. So you will expand for rotational kinetic energies. You will have 1/2 Ix omega x square plus 1/2 Iy omega y square plus 1/2 Iz omega z square. Now, the second joint does not have its joint velocity. However, please understand, it will have its omega x, omega y, and omega z. So, in other words, each and every joint will have a translational velocity, rotational velocity. You have to combine all those velocities to find the total energies. So you have to find the total kinetic energy and total potential energy. I hope that answers your question.
Yeah, what? Because when I did solve for the omega x, y, and z for the third joint, I believe it gives me like omega 2 sine of theta and omega 2 cosine of theta in my code. Or
I
that's the result.
I don't know without looking at your code, but you will get the values. So
Okay.
just I would follow the steps that we have followed for solving all the previous problems, and then you should be good.
Okay.
All right, I'm gonna stop sharing. Any other questions? If there are no other questions, then I will see you on Wednesday.